I'm going to be presenting the solutions for video problem 2 as created by group 3 on behalf of all of these lovely people right here. We're going to be starting off with problem A. So in problem A, we're given a function in the frequency domain, capital X1 of omega, which is defined as the rectangular function of omega over some constant w. Now, to start off, we want to visualize this function so that we can deal with it more easily. So we know that the rectangular function of omega over some constant w looks like this, where we have on this axis is the frequency axis, and this is our x of omega. And this is 1, this is 0, and this height is 0, obviously, it's the axis. And this is going to be w over 2, and this is w over 2. So we have a width of w and a height of 1. Okay, so now that we know what our function looks like, we can use the formula for the inverse Fourier transform to compute x1 of t, which we know is going to be equal to 1 over 2 pi times the integral from negative infinity to infinity of capital X1 over omega times e to the j omega t d omega. Okay, so this formula is just the definition of the inverse Fourier transform, and we can now apply it to this signal. So we know that for all values of omega greater than w over 2 or less than negative w over 2, this is going to be equal to 0, which means that it doesn't contribute at all to x of t, which means that we can rewrite this as x of t equals 1 over 2 pi times the integral from negative w over 2 to w over 2 of 1, which is the value between these two bounds, of e to the j omega t, d omega. And this is super easy because it's just integrating an exponential. So we know that this is going to be equal to 1 over 2 pi times, and then we divide by j and t, which are these constants being multiplied to omega. So 1 over j t times e to the j omega t, evaluated between negative w over 2 and w over 2. Okay, so now we just can plug in these values into our equation to get, take out the constant terms, we can take out the 2 pi j and multiply this by e to the j w t divided by 2 minus e to the negative j w t divided by 2. So when we look at this, we can notice that these two terms are actually complex conjugates of each other, which means that when we subtract them, we are going to get sine times like the magnitude. Here, I'll just demonstrate this. So if we have one term here, and this is the conjugate, when we subtract this, we are going to get an imaginary term over here that's equal to twice the sine term, which is the imaginary component of our term. So this is going to be equal to 1 over j t 2 pi times j 2 sine, and then wt divided by 2. And this just comes from this right here, which is the angle of our imaginary number. So now a bunch of these things will cancel out. So the j's cancel out, the 2's cancel out, and we're left with just simply or we could actually most easily write this way, sine of wt divided by 2 divided by t times pi. Now, at this point, we want to write it in terms of the sinc function. So we can define what sinc is equal to. So we say that sinc is equal to, for x is equal to 0, it's going to be equal to 1. And for x not equal to 0, it's going to be equal to sine x over x. So, at this point, we want to make this look like some sine x over x. And we know that we have sine wt over 2, so we want to make this bottom term have a wt over 2. So what we're going to do is try to get a wt over 2 term in the bottom. So we multiply both sides, both numerator and denominator by w over 2, so that we get w over 2 times sine of wt over 2 over wt over 2 times pi, which looks like w over 2 pi times sinc of wt divided by 2. And this is our answer to this, giving the inverse Fourier transform of this equation in terms of the sinc function. So that solves this problem.